In this video, I quickly want to go over some examples of solution preparation. Now, a lot of the other things in this particular section of the book are going to be covered on your worksheet, and I'm not going to go over everything in this video. Mostly just the first objective, the rest is on the worksheets. So the first thing I want you to know the difference between is that of a stock solution and a standard solution. So both stock and standard solutions contain a known concentration of the analyte. And the analyte is the component of a mixture you're interested in. So for example, if you're doing an analysis of copper, copper is the analyte. So the difference between a stock solution and a standard solution is that a stock solution is a solution that has the highest concentration of your analyte, and you will be using that solution to prepare the standard solutions. So there's usually no analysis done on a stock solution because that is always done on the standard solutions. So standard solutions are a set of solutions that contain varying but known concentrations of your analyte. So for example, if you are doing the copper analysis, you might make a 1, 2, 3, 4, 5 part per million standard solutions, and then those solutions will be analyzed along with your unknown solutions. And again, a standard solution is prepared from the stock solution. So the rest of this video is just going to be going through a couple of examples. This first one is a fairly simple example. So you would be trying to, in this case, make a sodium chloride solution at a specific concentration. So making 500 milliliters of a 1 molar solution. So the first step when you're trying to determine how many grams of sodium chloride are required to make this solution is to find the molar mass of sodium chloride, because you're starting from a solution of moles per liter and you're trying to figure out how many grams are required to make that solution. So if you look up the molar mass of sodium chloride, you will find that it ends up being 58.44 grams per mole. So for this particular example, we don't really have to do a calculation. So if you just think through it, if you're making a 1 molar solution, that means you're going to have 1 mole of sodium chloride per liter of solution. So we know the molar mass being 58.44 grams per mole. So if we were to make a 1 molar solution in 1 liter, then we would have to use 58.44 grams, okay, because that would be a mole per liter. But since we're doing it in 500 milliliters, that's half the volume, so you should need half the mass. So in this case, to make a 1 molar solution in a half a liter, 500 milliliters, we would just weigh out half that mass of sodium chloride, so we'd end up with 29.22 grams of sodium chloride to make 500 milliliters of a 1 molar solution. Okay, so example like this is fairly simple, and the next few examples will be a little bit more difficult where a little bit more calculation is required. Okay, so whenever we're doing a solution preparation, that usually requires some kind of dilution. So in this case, we have a stock solution of concentrated HCl. So the stock solution has a concentration of about 12.1 molar, and we're trying to make, we'll call it a standard solution, 100 milliliters of 2.5 molar HCl. So the question is, how much of the stock solution, how much of the concentrated hydrochloric acid is needed to prepare that particular solution? Okay, so whenever you're doing some kind of dilution, this is the equation to use. Okay, so C1 being the concentration of the stock solution, C2 being the concentration of the dilute solution that you're trying to prepare, V2 is the final volume of the solution that you're preparing, and V1 is what we're trying to calculate, which is the volume of HCl that needs to be removed from the stock solution and added to the 100 milliliters total volume to make the 2.5 molar solution. So if we were to write this out, we have C1V1 equals C2V2. So C1 is going to be 12.1 molar. And then we're trying to solve for how much of that we have to take out to make the 2.5 molar solution. Okay, and on the right-hand side of the equation, we have the concentration that we're trying to make, 2.50 molar. And what volume are we making that in? 100 milliliters. Okay, so now if we solve that equation, our V1 ends up being 20.66 milliliters. So what that's telling us is that we need to take 20.66 milliliters of the concentrated HCl, transfer that to a 100 milliliter volumetric flask, and then fill that volumetric flask up to 100 milliliters, and the resulting concentration will be 2.5 molar HCl. So the last example I have in this section is the preparation of an unknown solution. So we'll get into a lot more of these types of calculations as we go throughout the term, and this is more of a real type of analysis. So an example that is more realistic in terms of what you might be doing if you were in an analytical lab, for example, and doing an analysis. Okay, so in this example, the first step was to take a 1.25 gram sample of a copper ore. So copper ore would be something that contains copper, but there's a whole bunch of other stuff in there as well. And so that's going to be dissolved in acid and diluted to 250 milliliters. So in that 250 milliliter initial flask is going to be all of the copper that is in the ore. And then for analysis, we're taking 20 milliliters of that solution we prepared and then diluting that to 50 milliliters. And then we have done an analysis and found that the concentration of copper ends up being 4.62 micrograms per liter. And we're asked to figure out what is the weight percent of copper in the original ore solution, which is this guy right here. So let's just see how we would solve this type of problem. So I've written down near the bottom here a pictorial view of what this would look like. So another way that you can think of this problem, just to give you a picture of how it would look. So we have first a 1.25 gram mass of the copper ore was put into a 250 milliliter flask that was diluted to the mark. So now all the copper that was in our ore sample is in this flask. We'll call this flask 1. And then from this flask, 20 milliliters of that was put into a 50 milliliter volume. We'll call that flask 2. And from analysis, we know that the concentration of this is 4.62 micrograms per liter. And what we're trying to find out is the percent by weight of copper in the original ore sample. So we're going to be working backwards from flask 2, figure out what's in flask 1, and use that information to figure out what is in the ore sample. So let's just go through this step by step. So the first step is to realize that this is really just a dilution calculation. So we have two volumes in flask 1 and flask 2. We have one concentration, and we're just trying to figure out the other. Now normally you'd be trying to figure out what the dilute concentration is, but in this case we're trying to figure out what the concentrated concentration is. So our calculation is going to start with our C1V1 equals C2V2. All right, so in this case V2 is the total volume of our dilute solution, which is 50 milliliters. C2 is what we got from analysis, 4.62 micrograms per liter. V1 is the volume of sample that was taken from the 250 milliliter volumetric flask, which is 20 milliliters, and C1 is what we're trying to figure out. So if we were to write this out, C1 times 20 milliliters is going to equal our C2, which is 4.62 micrograms per liter, and that's multiplied by the volume of 50 milliliters. And if we run through that, we get a concentration of 11.55 micrograms per liter of copper in flask 1. So that makes sense because we would expect flask 1 to have a higher concentration than flask 2, because flask 2 was diluted from flask 1. So now step 2 would be to convert the concentration into a mass, because we need to know how much mass is in the first flask in order to determine the percent by weight in the copper ore. So we start off with our 11.55 micrograms per liter. Right, that's per liter, but we only have 250 milliliters in flask 1. So if we multiply that by 250 milliliters, or 0.250 liters, we end up with 2.888 micrograms. And we'll just keep an extra sig fig there to avoid any rounding errors. So that's how many micrograms of copper we have. Now the sample that we were given initially that we put into flask 1 was in grams, so we're going to convert micrograms into grams for step 3. 2.888 micrograms of copper times 1 gram per 1 times 10 to the 6 micrograms, and that equals 2.888 times 10 to the minus 6 grams of copper. So now we know how many grams of copper are in flask 1, and remember, since we put the copper ore into the flask 1, all of the copper that was in our ore sample is going to be in flask 1. So that's how many grams of copper there are. Now we have to figure out the percent by weight in the copper ore. So step 4 would be to do the percent by weight calculation. So percent weight by weight is going to be the mass of our analyte, the mass of the copper, 2.888 times 10 to the minus 6 grams of copper, divided by the sample mass, 1.25 grams of the ore, times 100%, and that is going to equal 0.000231% by weight copper in the copper ore sample. So as I said, this is a bit more of a difficult calculation, one that requires a bit more thinking, but we will get more practice with this as the semester goes on. But as for this section, this chapter, that's about all I have. So if you have any questions, please let me know.